Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 6 and polar coordinates. And today we're talking about Section 6.4, graphs of polar equations. So in this section, we'll use point plotting to graph polar equations, and we'll also use symmetry to graph polar equations. A polar equation is an equation whose variables are r and theta. The graph of a polar equation is the set of all points whose polar coordinates satisfy the equation. We use polar grids like the one in the figure to graph polar equations. And remember, I mentioned in the last section that you can download these off the internet. Just go to your favorite search engine and type in polar coordinate graph paper, and you'll get a whole bunch of choices that come up. All right, so we looked at a couple of examples of these in the last section, circles in polar coordinates. The graph of r equals a cosine theta and r equals a sine theta are circles. It says a is greater than 0, but actually a doesn't even have to be greater than 0. It's still a circle. I think if you make a negative, it may not come out looking exactly like the picture. All right, so for our first graphing example, let's graph the equation r equals 4 sine theta. When you graph a polar equation, theta is always going to be in radians. So we'll use the point plotting method, and we will use multiples of pi over 6 from 0 to pi to generate coordinates for the points. So we'll construct a partial table of coordinates for this equation, again, using multiples of pi over 6, and then we'll plot those points and join them in a smooth curve. So the part of this that I'm not going to spend a lot of time on is actually crunching these numbers. So you might want to pause the video and just make sure that if I give you these values of theta, 0, pi over 6, pi over 3, pi over 2, that you know how to plug those values into the equation r equals 4 sine theta. So for example, the sine of 0 is 0. That's how you got the 0 here. The sine of pi over 6 is 1/2. That's how they got the 1/2 here, and so on. So the first few points on the graph, remember these are in polar coordinates, are going to be 0, 0, 2, pi over 6, 3.5 comma pi over 3. Hang on a second, I see a typo there. Okay, we got that typo fixed there. That was just a little copy and paste malfunction, I guess. All right, there we go. Okay, so continuing with the table, remember we're using multiples of pi over 6 for theta. We're going all the way up to pi. Let's see, that all looks okay. So again, you're just plugging the value of theta into the equation. So again, just check to make sure that you're able to do this. All right, so what I'm going to do now is switch over to my tablet. And I'm kind of proud of myself. I figured out how to put these pictures in the tablet, and you can see I fixed that typo. All right, so I'm going to start plotting these points. Remember, they are in polar coordinates. Starting with 0, 0, that's the pole, also known as the origin. Okay, 2 comma pi over 6. So here is, let's see, which one would, 1, 2, 3, 4, 5, 6, that's pi, okay, so this would be pi over 6. All right, so there's 2 comma pi over 6. We're going out 2. Sorry, that keeps happening. 3.5 comma pi over 3. This is pi over 3 up here. Oh, wait a second. Hold on just a second. I don't think I've ever used this particular polar grid before. Okay, so I'm just trying to make sure I know which angle is which here. This is a little funky. Okay, so let's say this is 0. Whoops. So then 1, 2, 3, 4, 5, 6. That would be pi over 2. Yeah, so these are going in increments of, come on now. Okay. These are going in increments of pi over 12. So that means this is 2 pi over 12. This is 3 pi over 12, aka pi over 4. And we have 5 pi over 12. Oh no, 4 pi over 12. This is pi over 3 right here. Okay, we got it. All right. All right. So 2 comma pi over 6. Sorry, I guess that's going to happen every time. Wish I knew how to lock that in there. Pi over 3 is right here, and we're going to go out 3.5. Actually, I just noticed something. Okay. All right. Okay, so that's 0. So that means this first little circle here would be 1, which means this right here is 2. And then along pi over 3, we have 1, 2, 3.5 would be right about there. And then 4 comma pi over 2, 1, 2, 3, 4. Okay, close enough. Continuing, let's see. So that's 6 pi over 12, 7 pi over 12. This would be 8 pi over 12, aka 2 pi over 3. That would be 3 pi over 4. And then 10 pi over 12 would be 5 pi over 6. And this over here would be pi. All right, so 3.5 comma 2 pi over 3 would be right here. This is one of those moments where I really miss being face to face and using an actual whiteboard, right? Let's see. Okay. And then 2 comma 5 pi over 6, that would be right here. And then 0 comma pi, that's back at the pole. So this is supposed to be a circle. I'm going to do the best I can here. It's going to look something like, oh, that looks terrible. Okay, but I'm going to show you what it looks like on the PowerPoint. Actually, what I might do is look for a better polar grid. I think that's part of my problem. Okay, there it is. That's what it's supposed to look like. And you can verify that the graph is a circle by changing from polar to rectangular form. We went over how that works in the last section. Okay, so I just went on a search engine and found a polar graph paper that I think I will like a lot better. So hopefully the next few examples will go better. In the meantime, let's talk about symmetry. So there are 3 types of symmetry in polar coordinates. There's symmetry with respect to the polar axis, aka the x-axis. So if you look at this picture and you imagine that the point r theta is on your graph, if that means that r comma negative theta, which would be the mirror image across the polar axis, if those 2 points are always appear on the graph together, then that means you have symmetry with respect to the polar axis. So the way to test for that is to replace theta with opposite theta. And if you get an equivalent equation, that means the graph is definitely symmetric with respect to the polar axis. To test for symmetry with respect to theta equals pi over 2, which is the y-axis, again, look at the picture. Suppose the point r theta is on the graph. First, look at the angle opposite theta, which would be down here. So let's see. Get my circle up here. The point r opposite theta would be right about here. If you change the r to an opposite r, then that's going to be the mirror image of your original point across the y-axis. So the way to test for symmetry with respect to the y-axis, aka the line theta equals pi over 2, you replace r theta with opposite r opposite theta. And if you get an equivalent equation, then the graph is definitely symmetric with respect to that line. Now, a word of warning. When you do the test for symmetry in rectangular coordinates, these statements go both ways. So if you make the replacement and you do get an equivalent equation, that means it is symmetric. And if you make the replacement and don't get an equivalent equation, that means it's definitely not symmetric. Unfortunately, that does not work in polar coordinates because remember, there are an infinite number of different ways to represent any particular point in polar coordinates. So if you don't get an equivalent equation, that means you may or may not have that kind of symmetry. So it just basically means don't count on it. But you may end up having it after all. So you're going to see some examples like that. All right, and then the last, got to find my mouse here. There we go. The last type of symmetry is symmetry with respect to the pole, aka the origin. So again, if you look at this picture and imagine replacing r with the opposite r, that's going to give you the mirror image of that point through the pole. So if you replace r with opposite r and get an equivalent equation, that means you definitely have symmetry with respect to the pole. All right. So just remember the possible answers from these tests for symmetry are either yes, you have symmetry, or maybe. All right. These tests are never going to give you a hard no. All right. Okay, so the first example of checking for symmetry, check for symmetry and then graph the polar equation r equals 1 plus cosine theta. So starting with symmetry with respect to the polar axis, if you replace theta with opposite theta, remember cosine is an even function. So cosine of opposite theta is the same thing as cosine theta. Since you get the same equation from replacing theta with opposite theta, that means this graph is definitely symmetric with respect to the polar axis. However, when you check for symmetry with respect to theta equals pi over 2, and you replace r theta with, that's supposed to say opposite r opposite theta. That's easy to fix. Okay, they did it correctly. They just didn't write it correctly here. Okay. So your cosine of opposite theta is going to turn back into a cosine theta, but the opposite r is going to stay as an opposite r. So you don't get the same equation, which means this graph may or may not be symmetric with respect to the line theta equals pi over 2. See, the reason that we do these tests for symmetry when we're graphing is that it can save you some work. For example, knowing that this graph is symmetric with respect to the polar axis, that means I definitely don't have to plug in any values for theta between pi and 2 pi. Okay. All right. If it had also been symmetric with respect to the line theta equals pi over 2, I might have been able to get away with just doing values from 0 to pi over 2, and that's it. Okay, so it looks like I am going to have to go from 0 to pi. And then finally, with respect to the pole, okay, so this time I want to get rid of that negative sign because now I don't want it. What did they do here? Okay, hold on just 1 second. Okay, we got those typos fixed. That was a really, really bad copy and paste malfunction. So, of course, the symmetry, the test for symmetry with respect to the pole, that's supposed to say pole. There we go. Is that r theta and opposite r theta are both on the graph of the function. So if you start with r equals 1 plus cosine theta and you just replace r with opposite r, of course, that's not the same equation. You can tell that, but without even doing this, what they did here was just multiply both sides by -1. So since the polar equation changes when r is replaced with opposite r, this graph may or may not be symmetric with respect to the pole. All right, so I think this is the time where I switch back to the tablet. And I will get rid of that scribble there in just a sec. Oh. Okay, so this I think is a better grid. I just went and downloaded this one a couple minutes ago. So again, I'm skipping showing all my work with actually finding these values of r. You're just plugging in the values of theta. Okay, so starting with 2, 0. So when theta is 0, r is at 2. So that's over here. You know what? I just had an idea. No, actually, I don't think that's going to work. Never mind. Okay, pi over 6, 1.87. That's going to be right about here. Pi over 3, 1.5 is going to be right about there. Pi over 2, 1 is going to be right here. Yeah, I think this is going better. 2 pi over 3, 0.5, that's going to be right about there. 5 pi over 6, 0.13, that's very, very close to the origin. And then finally, 0, pi is right at the origin. And then remember that this graph is symmetric with respect to the polar axis. So if I draw this part, it's not letting me draw it. There we go. Then the bottom is just going to be the mirror image of that. So I will do my best to make another copy of that. Okay. All right, so I'd say that came out a little bit better than the first one I did. It would be even better if I was working on a real old school whiteboard. So let's go back and look at what theirs looks like. Okay, it looks like that. So that is an example of what's called a limaçon. Okay, it's a French word that means, an old French word that means snail. So there are a bunch of different kinds of limaçons. Let's see, I guess the kind we just did, A was 1 and B was 1. So if A over B equals 1, that gives you this kind here. That's called a cardioid, which is a heart shape. If this ratio A over B is less than 1, you get a limacon with an inner loop. If A over B is between 1 and 2, you get a dimpled limacon with no inner loop. And finally, if A over B is greater than or equal to 2, you get no dimple and no inner loop. It kind of looks like a circle that's been flattened on one side. All right, so the next example, we're going to graph the polar equation r equals 3 cosine 2 theta. Let me make sure I have the tablet ready for that. Okay, so r equals 3 cosine 2 theta. First, we'll check for symmetry. So for the polar axis, we replace theta with opposite theta. And once again, since cosine is an even function, that equation is not going to change, which means we definitely have polar axis symmetry. For the line theta equals pi over 2, we replace theta with opposite theta and replace r with opposite r. That equation changes, which remember means we don't know. There may or may not be symmetry. And for the pole, just replace r with opposite r. Again, the equation changes, so no guarantee whether or not we have that kind of symmetry. All right, so let's see. So completing the table of values, we'll go from 0 to pi. And again, I would urge you to pause the video and try this yourself. So now I'm going to switch over to the tablet. I think I thought of one minor improvement for how we can do this. Okay, so starting with the point 3, 0, when r equals 3, theta is 0. So I'll put that right there. You can see that dot a little better. 3 halves comma pi over 6 is going to be right about here. Pi over 4 comma 0, or 0 comma pi over 4, that's going to be at the pole. All right, now it starts to get a little tricky. Negative 3 halves comma pi over 3. That means we're going to start along the line theta equals pi over 3, I should say the ray. But instead of going positive 3 halves, it's negative 3 halves, which means we are going to mirror that point through the pole. So let me get rid of that point, and it's actually going to go right here. All right, and that brings us to negative 3 comma pi over 2. If it was 3 pi over 2, it would go here, but since it's negative, it's going to get mirrored through the pole and it's going to end up down here. Negative 3 halves comma 2 pi over 3. If it was 3 halves 2 pi over 3, it would be right here. But since it's negative, it's going to mirror through the pole and end up over here. And then 0 comma 3 pi over 4, that's at the pole again. So let me show you what we have so far. We started out at this point, and we went over here, and then we went down here, around this way, and now we are there. Okay, so continuing, let's see, we left off at 3 pi over 4, so now we're going to go 3 halves, 5 pi over 6, which is right here, and then 3 comma pi, which is over here. All right, so that's going to give us this. And then remember that this graph definitely does have polar axis symmetry. So if we draw the mirror image of everything that's there, we are going to get something that looks like this. I think this is the best one yet. All right, so that is called a rose because it kind of looks like a flower. Let me switch back to the PowerPoint. Yeah, I think mine looks almost just like that. So that's an example of a Rose curve. Any equation of the form r equals a sine n pi or r equals a cosine n pi is called a Rose curve. Interestingly, if n is even, the rose has 2n petals, but if n is odd, then the rose has n petals. So here are some examples: a rose with 4 petals, one with 3 petals, here's one with 8 petals, and here's one with 5 petals. All right, and the last example is r squared equals 4 cosine 2 theta. So running through the test for symmetry, replacing theta with opposite theta. Again, cosine is an even function, so that equation does not change. And because of the r squared, when you replace theta with opposite theta and replace r with opposite r, once again, the equation does not change because the square of opposite r is the same thing as the square of r. And the same thing if you just replace r with opposite r. So this equation has every type of symmetry, which means that we only need values of theta from 0 to pi over 2, because then we can use our symmetry. All right, so replacing theta with 0, we get r squared equals 4 times 1. So if r squared is 4, that means r is plus or minus 2. And then replacing theta with pi over 6, the cosine of pi over 3 is 1/2. 4 times 1/2 is 2, so r squared is 2, which means r is plus or minus square root of 2, about plus or minus 1.4. And if you replace theta with pi over 4, you get 4 times cosine of pi over 2, which is 0. All right, so switching back to the tablet one last time. And you can hear one of my birds there in the background saying hello. All right. So first, 2, 0 and -2, 0 are those 2 points. 1.4, pi over 6 is going to be right about there. And -1.4, pi over 6 is going to be right about here. And then 0, pi over 4, that's going to be at the pole. And because this, so what we have so far is something like this and something like this. And because we have every kind of symmetry, including polar axis symmetry, we are also going to have this and this. So it's kind of like a figure 8. That graph is called, let me show you. Whoops, that's called a lemniscate. So any equation of the form r squared equals a squared sine 2 theta or r squared equals a squared cosine 2 theta is called a lemniscate. The kind that we just looked at has every type of symmetry: polar axis, theta equals pi over 2, and the pole. If it was sine instead of cosine, that only has symmetry with respect to the pole. And that's going to do it for section 6.4. We'll see you next time.